Have you ever faced a complex problem in programming or everyday life and wished there was a smarter, more efficient way to solve it, rather than just brute forcing your way through endless trial and error that wastes so much time? That's exactly where dynamic programming comes in. It's a powerful technique in computer science that helps us tackle even the most intricate challenges by breaking them down into smaller, manageable pieces that can be solved systematically. At its core, dynamic programming isn't about any kind of magic at all. It's fundamentally about achieving efficiency and cleverly avoiding those redundant calculations that plague naive recursive approaches. Imagine you're building a tall tower with colorful Legos on the floor. If you keep rebuilding the exact same section over and over again each time you need it higher up, it takes forever and becomes incredibly frustrating. Dynamic programming teaches us to build each unique section just once, save it securely in place, and then reuse it efficiently whenever it's needed later in the construction process. This smart approach relies on two fundamental properties that make it work so well: optimal substructure and overlapping subproblems, which together enable us to optimize solutions dramatically. Optimal substructure means that an optimal solution to the overall problem can be reliably constructed from the optimal solutions of its smaller subproblems, creating a solid foundation for the whole. Think of it like a perfectly designed sports car. Each individual part, from the powerful engine to the aerodynamic wheels, is optimally engineered to work together and make the entire car perform at its absolute best on the track. Overlapping subproblems occur when a typical recursive algorithm ends up repeatedly solving and recomputing the exact same subproblems multiple times, leading to massive inefficiency. A classic real-world example is calculating the Fibonacci sequence, where to find the fifth number f, you first need to compute f and f, as each term is the sum of the two preceding ones. But then to find f, you also need f and f, so you can see that f ends up being calculated twice in this branching process, and it only gets worse for larger numbers. Dynamic programming effectively tackles this redundancy head-on using two main proven techniques: memoization for top-down efficiency and tabulation for bottom-up solidity. Memoization is an elegant top-down approach where you start from the main problem and work downwards. It's like keeping a detailed diary of all your previous calculations to reference quickly. When you encounter a subproblem during recursion, you first check your diary to see if the answer is already there. If it is, you simply use that saved result without recomputing. If the answer isn't in the diary yet, you calculate it step by step, write it down immediately for future use, and then proceed, ensuring no subproblem is ever recalculated unnecessarily. Tabulation, on the other hand, takes a structured bottom-up approach. It's like methodically filling out a comprehensive spreadsheet row by row and column by column. You begin with the simplest, base case subproblems at the start and systematically build up, using previously computed values to solve increasingly complex ones in a logical order. Each individual cell in your spreadsheet neatly represents the optimal solution to a specific subproblem, and you fill them in a precise sequence so dependencies are always resolved first. This guarantees that by the time you reach the cell for the full original problem, all its necessary subproblems have already been solved accurately and are readily stored for instant access. Dynamic programming proves incredibly versatile in practice, finding applications across diverse fields from sophisticated financial modeling to cutting-edge bioinformatics research. It powers optimizations like finding the fastest routes in GPS navigation systems, computing the absolute shortest path between two distant points on a map, and even helping predict volatile stock market trends with greater precision. Consider the classic coin change problem, where the goal is to find the minimum number of coins needed to make up a specific target amount using given denominations. Dynamic programming solves this by systematically building up optimal solutions for every smaller amount from one up to the target, ensuring the fewest coins are used at each step along the way. Ultimately, it transforms problems that might otherwise require an infeasible exponential amount of time and computation into much more practical and efficient polynomial time solutions. This kind of efficiency is absolutely crucial in today's fast-paced, data-driven world, where the ability to process massive datasets quickly and accurately is often the key to success and innovation. So, the next time you encounter a problem that seems completely overwhelming at first glance, Remember the power of dynamic programming as your go-to strategy. It's not just another coding technique tucked away in algorithms class. It's a profound way of thinking that equips you to break down overwhelming complexity and craft elegant, highly efficient solutions every time. By truly understanding its core principles like optimal substructure and the two implementation methods, you gain a powerful, timeless tool for tackling some of the toughest challenges in computer science and far beyond.